that, let's talk about properties of the natural log. This is what we were talking about last time. So I will refresh your memory. The definition of the natural log is this. This is somewhat strange. This is probably not the definition that you used when you first learned about logs in high school, if you did. Typically, logarithms are presented as an inverse operation to exponents, that's also true. But this is the way that we are going to present logarithms because it's a little nicer from an abstract point of view. The natural log is defined in this way. That is the area under the curve of the function 1 over t. All right, and some basic properties that we talked about last time. I will just refresh our memory here. First of all, the derivative of the natural log of x is 1 over x. That's because this integral formula here, if you take the derivative on both sides, on the left it says derivative natural log of x. On the right it says derivative of the antiderivative of 1 over t. And the derivative and the antiderivative sort of cancel each other out. That's called the fundamental theorem of calculus part 2, sometimes people say. Or part 1, I can never remember which is which, but anyway, when you take the derivative on this side, it cancels the integration and you get just the original function 1 over x. Okay, that's one important property. And then also other important properties that we talked about were the natural log of 1 is 0, and the natural log of a product, a times b, is ln a plus ln b, all right? All of these things can be proved directly using the definition up there and some simple tricks. All right. I have 3 more simple properties of the natural log of the same sort of general type as these, and then we will get onto something else. But anyway, all of these things you should definitely memorize, I suppose. Although I think these are things that everybody. Hopefully you've seen these before. Okay, a few more simple properties like this. Let's consider dividing. Here's a very simple kind of dividing. What if we do the natural log of a divided by a? Of course, a divided by a is just 1, right? So that's the same as ln of 1, which is 0. That's one of the things we already said in the box. But I could also do, instead of making that a 1, I could make that a times 1 over a, and then split this up using the other thing in the box there about multiplication inside. It will say ln a plus ln of 1 over a, all right? And all of these things are equal, right? Because I started with ln of a over a both times. What that means is if you read this this part must equal 0, right? Because all of these are equal in this way. So that means ln a minus plus ln 1 over a equals 0, and you can solve that for ln a. Negative ln 1 over a. This is another basic property of the natural log, which you've probably seen before. Maybe it's actually better. Sorry, I meant to write it the other way around. These are equivalent, but it's usually written in this way. ln of 1 over a equals negative ln a. They're the same, but that's a little more convenient. So this is another rule that you can use to simplify natural logs. If you have something, the reciprocal of something, its log is the opposite of ln a. All right? That's all of that was starting with a over a, but in general we can do also something like the natural log of a over b. There's a formula for that, and this follows directly from what we've already done. You can separate a over b is the same as a times 1 over b, and then split that up. Remember, log of product is log of the first thing plus log of the second thing. And then that second thing, I use the thing that I just wrote above in the box. This is the same as ln a minus ln b, all right? And so overall it says ln of a over b equals ln a minus ln b. Great. right? These are all basic properties of the natural logarithm function. And I got one more, and then we'll talk about other things. What if you do the natural log of like something to a power? That's what I want to talk about. Maybe I'll just first of all talk about what would ln of a squared be? Anyone want to suggest how could we simplify that using the rules that we've already got? I would like to somehow rewrite the a squared as something else. Yeah?
Is it 2 ln a?
It is 2 ln a, yeah. How do you get there? Other than you already know the rule.
I don't know.
Any ideas? You can actually get there by writing this in a different format. Did you have another idea? No. You were just going to tell me the answer? It's true, the answer is 2 ln a, yeah? Yeah, it's ln of a plus ln of a. To write one additional step, you could write this as a times a, first of all. That's what a squared is. A squared is a times a. And then you break that up using the like a times b rule that we had above. It'll just say ln a plus ln a. And that is 2 ln a, right? So it is true that ln of a squared is 2 ln a. What if it was a cubed? Actually, you can do the same thing. If it was a cubed, I'm not going to write this down, but if it was a cubed instead, you would go a times a times a, and then you add them together, but there'd be 3 of them, and you get 3 times ln a. So really, ln of a to any power is that power in front times ln a. I'm going to write that. And this is our last sort of important rule about the natural log, is this. ln of a power of a is n times ln of a. And this is actually true even if the n is not a whole number, although I don't want to get into the details of that, but this is true for any real number a, all right? Even if n is what I meant to say, any real number n. The exponent, I mean, it's also true for any, I suppose, positive number a, but any real number n, right? This exponent, it doesn't just have to be 2 or 3. It could be something like a half, which would be like a square root is a half power, or negative powers, or anything. It could be anything. True for any real number. All right? So these are the important properties of the natural log. Actually, this last one is quite useful when you're, like, for the sake of using logarithms to solve problems that you might encounter. I actually, I'll tell you a little story about this someday, but I actually used the natural log in my real life once. Have any of you actually used logarithms in your real life? This is true. I did once. Yeah, I'll tell you about it someday when you're older. Anyway, these rules, we can use them kind of all together, and you'll see some things on the homework next time around. Something like we can simplify stuff involving logs using some kind of combination of these rules. For example, can we simplify the natural log of square root of x sine x? Simplify that as much as we can, all right? First of all, how shall we handle the square root? Any ideas about that? Actually, none of the things, you have to look at the various properties in boxes that I wrote up here. None of them have a square root in them, but actually we can handle the square root using this stuff, yeah? Yeah, the square root is a 1/2 power, and so actually it is going to be handled by this property here. We write the square root instead as an exponent of 1/2, which is really like, in this class at least, you basically always want to, if you ever see a square root, you should probably change it to a 1/2 power. Anyway, now we use the rule, which you can see in the box right there. You bring the exponent down, and it becomes a coefficient in the front. So this will say 1/2 natural log x sine x. All right, can we do anything else? Actually, we can simplify a little bit more using one of the other rules up there. Any suggestions? Yeah?
Could you separate it into ln x and ln sine?
Yeah, I have a product on the inside. This is x times sine of x. And so we can split that into 1/2 ln x. Well, let's just keep the 1/2 out there and then split it up. Ln x plus ln sine of x. Great. This is a little weird. Ln of sine of x. All right. And I think that's about as good as it gets. I mean, you could distribute the 1/2 if you like, but there's no more real simplifying that you can do here. Anybody feel like can I here do like ln of sine plus ln of x? What are your thoughts about that? Dr. Sonic is calling me. Sorry. Decline. Somehow when I share my iPad like this, it doesn't show any notifications. Like you don't see like my wife texting me, but you see if someone actually calls me. That's the lady, my mouth doctor. I'm doing much better, by the way, in case you were concerned. Anyway, what about this? Anybody have any feelings about this? This was sine and x. Can't you split it up like that? The answer is no, you should not do that. What's the problem with that? No? You got problems?
I feel like it's because it's sine of x, not, well, you can also write it as the sine of x in parentheses, so because of that, you can really split it up.
Yeah, the splitting up is what you do when you have a product. So the rule that I was allegedly using is this one right here, right? But this is for A times B. You have to have something times something else on the inside. This is sine of x. It's not sine times x. And actually, sine times x doesn't even make any sense. Like sine is a function that you plug something into. You don't do sine times something. And in fact, like this right here, ln sine, this is actually totally bogus. This doesn't mean anything. Ln is a function, sine is a function, and nothing is being plugged into it. This is nonsensical. So don't do that. All right. This is like you can't just have sine all by itself. This sine of what is what I would say. All right. This is kind of like nobody would ever do this, but this is like if I have what is square root of x divided by x? Can I just like cancel the x's and I get square root, right? No. There is no such thing as square root of nothing, right? Square root is a function. You can't just get square root. So this is all bogus too. All right, anyway, don't split this up any more than that. You can't. All right, let's talk briefly about the graph of ln x as a function. And then we'll talk about some like more traditional sort of calculus type things that you can do with it. The graph of ln x as a function. All right, you have to remember the definition of ln x is this, right? It's the integral 1 to t of 1 over t dt. And remember what that means is it's the area under the curve of this function 1 over t. So it is this sort of this area here where this goes from 1 up to, sorry, I put too many t's. It should be at x up here. Sorry about that. The upper boundary on the integral is x. So if you have some number x and you want to take the natural log of it, it means you take the integral from 1 up to x, whatever that number x was, all right? But this what I drew here is not the graph of ln x. This is like how you define ln x. It's that area. But what is the actual graph of ln x looks like? So we already know that ln of 1 equals 0. So over here, I'm going to draw a graph of ln x. This is the graph of ln x. ln of 1 is 0. So whatever this thing is, it has to go through that point. And also, we talked about how the natural log of a number bigger than 1, the answer will be positive, and a number less than 1, the answer will be negative. And you just have to think about, as we move x, like in this picture, as you move x further and further to the right, this area increases, and it is positive, right? This area is always positive from 1 up to x, and it just increases as x increases. And so the graph of ln x over here, it increases as x increases. It does something like this. It increases. You have to think about, how is this area going to change as x moves to the right? And the answer is this area gets bigger, although it gets bigger kind of like at a slower and slower pace, just because this area, like the function here is so small that the area does increase as x increases, but not very quickly, all right? That's why I had it going up, but it's not like going up like a parabola would. It's going up kind of slowly. All right, and then what if I move x to the left of 1? Then this area counts as negative, and actually this area becomes very negative very quickly because this is going up to infinity. So I'm going to try and draw that. What I just said, it's negative and it becomes very negative very quickly, like that. All right. This is the graph of ln of x. This is a picture I suppose you should, I don't know about memorize. I mean, you should know that the graph of ln x looks like that. It goes through 1 here and 0. It doesn't really go through other special points, but it goes up and to the right, and it goes sort of down towards the y-axis like that. All right. I will just say, I mean, you can tell by looking at the picture here, but the domain of this function is the interval 0 to infinity. That is, you cannot plug negative numbers into the natural log. That is undefined, all right? That's why this graph doesn't exist on the left side of the y-axis. All right, great. What about some other values? Is there anything else that we can say about values of this? There's really not all that much that we can say about the values of this, although because you're looking at this, you can tell that this curve goes up forever over here. And one thing that is interesting and important that we are going to talk about is you could ask yourself, when does that graph go through 1? Like, it does have to go through 1 at some point. For which x value is the y value equaling 1 here? So I will say there is some point, there is some number x with ln x equals 1, right? It would be, on my picture, it would be like right around here. There has to be some number there where the graph goes through y equals 1. And that number has, it's not like any, it's not like 2 or something like that, but that number has a special name, and this is called, anybody know what I'm talking about here? This is the number e, yeah. So this number, this is the number e. And its value, you know, e is kind of like pi in that it's an irrational number which has sort of digits that go on forever without repeating. Its value is something like 2.7, I wrote this down, 2.71828, etc. Right? I don't have the digits of e memorized. For some reason, like it's kind of it's classy to memorize digits of pi, but nobody cares about the digits of e, although e is like just as important as pi as a mathematical constant. All right, it's super important and it comes up all the time in calculus. The way that pi comes up all the time in geometry, like e has a similar stature in the area of calculus. All right, great. This is what e is. Let's talk about, we're not going to talk about e very much more right now, but e is going to be super important as we go forward. Let's talk about derivatives and integrals using ln of x. All right, still on the topic of the natural log. Derivatives and integrals using the natural log of x. So the important properties that we have talked about are this. The derivative ln x is 1 over x. All right, this you absolutely need to know. We will be using this often, and along with this as a derivative property, you get sort of for free an antiderivative property. If the derivative of that is that means automatically the antiderivative of this is this. So that means the antiderivative 1 over x dx is ln of x plus c. All right, that is also a property that we're going to be using all the time. The antiderivative 1 over x is ln of x plus c. But let's talk about derivatives first, and then we'll do some antiderivatives. Obviously, like that is the derivative of ln x. These can be a little bit more interesting when you have sort of other stuff going on with the ln of x. If we have something like ln of, other stuff, not just x in there, and I'm trying to take the derivative. Sorry, I left that out. If I'm taking the derivative of ln of some other stuff, then we must use the chain rule. And this is typically pretty straightforward as long as you remember how to do the chain rule. I got a few examples, but basically you could say, like, generally speaking, if you're in the mood to like memorize formulas or whatever, how does the chain rule work itself out in this situation? If you have the derivative of ln of some other stuff, which I'll call g of x, what is that? The chain rule, I hope everybody remembers, means you do the derivative of the outside part first, keeping the same thing inside, and then you multiply by the derivative of the inside. What that looks like in this case, I said do the derivative of the outside part first. That's the ln. So the derivative of ln whatever is 1 over whatever. So when I do the outer derivative, I get 1 over g of x. I'm just using this formula here, but instead of x, I'm using g of x. All right? That's the derivative of the outer part, the ln. And then the chain rule says times the derivative of the inside part. So it's that separately times the derivative of the inside, which is g prime of x. All right? Some people write this you could write it that way. You could also make just like a single fraction out of this. So sometimes you will see this formula written in like big lists of formulas. Derivative of ln g of x is equal to g prime of x over g of x. If you like, you can memorize that. Although to me, I don't really have this memorized per se. I just do the chain rule. It's not all that taxing. And generally speaking, I don't really like memorizing a bunch of stuff. So I prefer to just remember to do the chain rule. But anyway, can we just do a few examples like this? So for example, derivative of something like ln x squared plus 5x minus 1. What is it? Well, you could use the box there. The g is just that quadratic polynomial. Or you could do the chain rule. I'm going to just do it like using the chain rule step by step, which is basically the same as the box. I do the derivative of the ln part, which gives me a 1 over something. So this becomes 1 over x minus 1. That's the derivative of the ln part. The derivative of ln x is 1 over x, so the derivative of ln something else is 1 over something else. And then times, this is the chain rule part, times the derivative of the inside. Can anybody say? Somebody shout it out. The derivative of the inside here? 2x plus 5, yeah, I agree. 2x plus 5, like so. All right, that's all there is to it. You could write that as a single fraction if you want to. I don't really care. How about, here's another derivative of ln square root 3x minus 5. This one has kind of an extra sort of double chain rule or something. Maybe, first of all, we could write this as a 1/2 power, of course, because I always do that. Ln of, I don't need parentheses here, 3x minus 5 to the 1/2. All right? Let's take the derivative of that. Here we're going to use the chain rule twice because I have a thing inside a thing inside a thing, right? There's the outside is ln, then I have this 1/2 power, and then inside of that I also have 3x minus 5. So we can handle it though. I do the outermost thing is the natural log, And so the derivative of the outermost thing is just going to be 1 over all that other stuff, 3x minus 5 to the 1/2. And now because of the chain rule, I have to multiply by the derivative of the inside, meaning now at this point the inside is just this much, right? The inside of the log is that much. And how do I take the derivative of that? I'm going to have to use the chain rule again. Any chain rule experts out there? Can you say what should I get next for the derivative of that inner part? You don't have to be a chain rule expert. Though it doesn't hurt. What do you say?
Would be 2 times 3x minus 5 to 1/2.
That is close. I think I would say instead of 2, it's 1/2. This, when you're doing the derivative, so this comes down as a coefficient. Is that what you meant to say? 1/2, sorry. 1/2, 3x minus 5. And what's the new exponent? You should subtract 1 in the exponent here. Negative 1/2, yeah. I think that's what she said. Great. That's the derivative of like the red thing there. I hope everybody remembers how to do the chain rule in that kind of a situation. You bring the exponent down to the front, and then you decrease the exponent by 1, leaving the same thing on the inside. And then finally, the final derivative of the inside, the very inside being 3x minus 5, the derivative of that is 3. So it's like that. This is what you get. This you can simplify if you want to, although I don't really care about that. Any thoughts about that one? This is a kind of doubly nested chain rule. All right, one more. This is actually a very easy one, but it's somewhat interesting. I want to do the derivative ln of minus x. This is easier than the 2 previous ones, I guess. It would be 1 over minus x. That's the derivative of the outside part, and then times the derivative of the inside. Derivative of negative x is just negative 1. So it's like this. All right. And that, ordinarily I wouldn't care about simplifying, but I actually want to simplify this just because I'm trying to sort of make a point here. So, derivative of ln x equals 1 over x, and also, apparently, because of what I just said, derivative of ln negative x equals 1 over x, right? This is the property that we've all been using all along, but then the example I just did, also the natural log of negative x is the same answer, right? 1 over x is the derivative of the natural log of x, and also negative x. Oftentimes, sort of realizing this, what this means is when you're taking the natural log of something, it doesn't matter if it's positive or negative. You get the same answer, right? That's one way to interpret these two things. Another way to write that is like this. So the derivative of natural log absolute value x is 1 over x. This is often how this property is written. The absolute values refer to the fact that actually it doesn't matter on the inside of the log there. It doesn't matter if the x is positive or negative. You're going to get the same answer either way. All right. So if you like, you can put this in another box or something. This actually, most of the time, people don't really care about the absolute values in this formula. They become a little more interesting, though, when you are doing the antiderivatives. So let's talk about integrals. And it's all based on this. Says the derivative of this is 1 over x. That means the other way around, the integral of 1 over x is that thing. So this is how this formula is typically written. The integral of 1 over x is the natural log of the absolute value of x plus c. All right. Actually, I wrote this a few minutes ago, but I didn't say the absolute value part. So if you leave the absolute values off, it's still correct. Although this formula, generally people like this formula better because this formula, you are allowed to plug in negative values for x and it's still true. Everything works If you don't write the absolute values, then you're talking about a function which has a smaller domain. And so this version with the absolute value signs is typically what people use rather than the other one. All right. Anyway, that's the basic formula that we use when it comes to integrals. Another way that this comes up, another way of writing the same thing would be this. Of course, 1 over x is the same as x to the minus 1, right? So this is another way to write the same formula. What it means is when you're doing integrals and the exponent is minus 1, actually you don't use the normal rule. So when we see, I'm just going to point this out, when the exponent is negative 1, you don't do, ordinarily if you have a power of x, you do this thing, right? You increase the power by 1, and then you divide by the power in the front, right? But when the exponent is negative 1, you don't do that rule. You do instead this rule. Why don't you do this? Well, if you think that through, if the if the exponent really was negative 1, then this would look like 1 over negative 1 plus 1, which is 1 over 0, which is not allowed. So if you tried to use this rule, it wouldn't work anyway because you'd end up with a dividing by 0. Instead, this is the appropriate rule to use when the exponent of something is a negative 1. All right, let's just try some examples. So that's the basic formula. And if you ever just see 1 over x inside of an integral, the answer is just going to be the natural log of the absolute value of x. This becomes more interesting when it is in the context of u substitutions. So let's try a few of these. I will say this comes up in u substitutions. Most commonly, I will say u substitutions with a denominator. For example, I got one here, and then I have a couple for you all to try. How about dx? 3x over 4 minus x squared dx. U substitutions with a denominator. All right, now we are going to have to do a U substitution here. The typical approach is to let U be the thing on the inside of something or other. I don't really see inside of anything, but if you don't see it inside but you have a fraction, I will say generally let U equal the denominator. Although that's not a hard and fast rule, and actually sometimes you have to do it in a slightly different way. But as a general principle, this will often work. Let U equal the denominator. So let's try that. I'm going to say U is 4 minus x squared. Can somebody say what's the du going to be? I hope you all remember how to do the U substitutions. People did, for the most part, did this great on the quiz. Yeah? Yeah. Negative 2x dx. Great. That's the derivative of u, and you put a dx on it. All right? Excellent. As I usually do, I'm going to divide the constant to the other side here. So here I'm going to say this is the same as negative 1/2 du equals x times dx. Right? That's the dividing the constant trick. Okay, now let's try to plug stuff in when I'm doing my U substitution. Towards that end, I find it a little nicer to write this using a negative 1 power. Well, anyway, first I'll just put the U where it goes. The U was the denominator, right? Like I said, in order to complete the substitution, I find it easier to write this with a negative power. So this would say 3x u to the minus 1 dx. And now can we change everything in, I don't want to see x's anymore, right? I want to see everything in terms of u's and du's. I would say, first of all, to simplify here, you can just bring the 3 all the way out of the integral. Multiplication by a constant on the inside, you can take it all the way out. So 3, integral. And then I have x u to the minus 1 dx. I like to write the u stuff first. just to gather my x's together. And what happens with that? You can see x dx is part of my substitution up here, right? X times dx is -1/2 du. So that's what I'm going to put right here. As usual, I'm writing many intermediate steps here. If you know what you're doing, you could probably skip over a lot of those steps that I just wrote, but this is how we do the substitution. And the last thing I would do before taking the integral is bring that constant out of the integral again. I have -1/2 multiple inside the integral. We can pull that out. So I think now I'm already, this is fully simplified, ready to actually do the integral. All right, and when we do the integral, u to the -1, it is, you can see it at the top there. Integral of x to the -1 is ln absolute value x plus c. So this is going to be -3/2 ln absolute value of u plus c, like that. Right, and then the u, last step, plug the original variable back in instead of u. So u was 4 minus x squared. So this, my final answer, 3/2 ln absolute value 4 minus x squared plus c. There you go. All right, this is a u substitution where we end up with a natural log. Sometimes the natural log can sort of appear when you're least expecting it, right? We started with something that looks kind of like a polynomial. I mean, it's a fraction, but the function we began with had nothing to do with the natural log, but it ends up appearing inside of the answer, all right? Not a huge surprise because the definition of the natural log the natural log is supposed to be an integral of 1/t somehow. So this, it's not so surprising that this ends up being equal to some kind of natural log of something. All right? Yes?
I'm sorry. Where'd you get natural log from?
It comes, yeah, it's, so this step right here where the ln appears, it's because I did this integral and using this rule here. The integral of something to the -1 is ln of that thing. Yeah.
Thank you.
That's where it appears. Great. I have 2 for you all to try. And then we'll talk about a little something else. 2 for you to try. Integral of tan x. This one actually really doesn't look like it's going to involve a natural log at all, but my hint for this is you should start by writing that as a fraction, and I hope you all remember there is one standard way to write tan as a fraction. And then another one here. See what you think. I'm going to come around and see how you feel. there's no way to
Yeah.
do anything with that. So good here. It's not long, although it's not gonna work.
Yeah, it's fine.
Yeah, although the fact is that this is not correct. Yeah, it's really LNX.
It's okay. Oh, it's right there.
Yeah, there's another X in there somewhere. But anyway, it's not gonna work right because you're gonna have an extra LNX. Do anything with this, so yes, is it not right? It's not that. Good here? Yeah, that's great. Let's go to 9. Yeah, this is the right track. That's right, so you can. This is the other side. This LNX divided by X, and instead write as LNX, not
Yeah. And then,
and then this part is here, this part is here. So it's worked out nicely. It's over here. Yeah, that's good so far. It's, yeah, sorry, this, use LNX to do the interpreted of that, which is important. Look over here.
Is that just?
That's the end. How's it going? Just got uh-huh. Yeah, you follow the
LNX squared over 2 plus.
Actually, you did it. It's not really possible. That is simple. So this example, you should choose the number. So like your choices for you are X or LNX. If you choose X, then it's stuck. So track the other. Still good here? This is great until right there. It's not that. When you do the angle of u, you have to do the angle of u. Think of that as like u to the 1. And then you change the exponent. It's just like if you do the angle of x to the 1, the answer would be 1/2 x. That's what you should do. And then there's one last step where you put the x's back in. Just try to do that step by once.
Okay, let's talk about these. I think most people, well, pretty much everybody I saw figured out the first one. Who tried it? Some people tried to do the second one first. The second one, I don't know if it looks easier. I would say it's not. The first one, the integral of tan x dx. Tan x is sine over cosine. I hope everybody remembers that. And once you make that fraction, it should occur to you to do a u substitution using the u as the thing on the bottom. So I say u is cosine x. That means the du is the derivative of cosine, which is negative sine x dx. And then this, the integral of all of this, it turns into, I have sine x on top and u on the bottom with a dx there. Separate these out as I like to do. I'll write this as u to the minus 1 times sine x dx. And then what do I do with sine x dx? That is negative du, right? If you move the minus sign over here. This says integral u to the minus 1 times negative du. And that is minus integral u to the minus 1 du. I hope everybody's with it so far. And what is the integral of u to the minus 1? It is ln absolute value u. So this says minus ln absolute value u plus c minus ln absolute value plugging in for the u. U is cosine x. There you go. That's it. All right. Pretty much everybody worked that one out as I was walking around. Any questions about that? I was talking to my kid last night, who is in high school. He's taking AB calculus now. So I ask him every so often, "Oh, what are you doing?" He said yesterday. He said, "Oh, we remembered, or we talked about don't forget the cupcake." Anybody familiar with this? So often I talk to both of my kids, especially when they were younger. I talk to them about what they're doing in math, and sometimes they say stuff that I've never heard of, or they have some kind of tricks for doing something, and I've never seen this or that trick. Don't forget the cupcake is what their teacher says. None of you have heard that? I asked, like, did your teacher make this up, or is this like a thing that kids say nowadays? That is referring to the plus C. Don't forget the plus C. They say don't forget the cupcake. This is what those kids are talking about in high school these days. Maybe it was just his teacher. I don't know. I don't forget the. It's either don't forget the cupcake or remember the cupcake. I don't know which is better. I couldn't find anything on the Reddits or anything about that. So maybe his teacher just made that up. Anyway, that's the one. What about the other one? The other one was ln x divided by x dx. And this one is a little bit deceptive. Generally speaking, you want to choose the u to be the denominator of the fraction, but in this case, that actually doesn't get you anywhere. Some of you I saw tried to do this. I'll do this in red because this is not exactly wrong, but it's just not going to work. If you choose u to be x, then the du is just dx, like 1 times dx, and then you can transform this as integral ln x divided by u du, and then that, I suppose you could write as ln x times u to the negative 1 du. But anyway, the big question at this point, you are looking at that and saying, what am I supposed to do with that? This does not relate at all to the stuff over here. And this is when you should realize, if you ever are doing a u substitution and you get into a situation like this, where there's like leftover bits that don't actually fit into the substitution at all, your conclusion should be, I guess I chose the wrong thing for the u. That's what happens when you choose the wrong u. So don't do that. I mean, it wasn't a bad idea because generally speaking, you should choose the denominator, but just sometimes it just doesn't work. And what you should do instead, I guess, is choose the numerator. Like there really isn't any other options in this case. I'm going to choose u equals the numerator, ln of x, all right? Wow, what's all the other stuff? That means the du is 1 over x dx. That's the derivative of ln x. And actually, I do feel good about this because I see ln x is here, and then the rest of it is x in a denominator, which is that. So I'm feeling pretty good about this. How I would write this substitution out, I would say this is integral u over x dx. And then if I separate that out, it's u times 1 over x dx. And that is exactly du. So it just says integral u du. and the substitution is complete. All right, this is a little weird. You may find yourself wondering, what am I supposed to do with integral u du? But this is actually an easy integral. This you think of as u to the power 1, and how you handle a integral of u to the power 1 is you increase the power and then divide by the new exponent. So this becomes 1/2 u squared. Don't forget the cupcake. All right, and then I replace the u with the original variable as always. 1/2 ln u, x squared plus c. There you go. I hope you worked that one out. I saw a lot of people got that one as I was walking around. Any questions about that? So sometimes the like the typical choice of u just ends up not working. You have to try something else. That's how the u substitution goes. All right, we got about 20 more minutes. I think that's enough time to talk about one more thing. How about one last thing about the natural log? I would like to talk about what they call logarithmic derivatives. This is a somewhat weird strategy for taking the derivatives of complicated things using logarithms. And I'll just do one example, and then I have one for you to try. It's not hard to do, really. It's just slightly strange. How about, this is, I will just say, a trick for avoiding sort of a big chain product quotient rules. Right? Actually, it is possible, if you know about using logarithms in this way, you can actually never do the product rule or quotient rule again. Although I wouldn't necessarily suggest always doing it this way. But if you have a situation where you are going to have to do a sort of big and nasty product rule or quotient rule, you can instead do it in this way. This is called the logarithmic differentiation. Anyway, here's an example. Y equals x squared, let's say 7 plus x to the 10 over 5x squared minus 7x plus 4. All right. Now this one, you could take the derivative using the chain rule, product rule, quotient rule. This is really a pain though, because it is overall a quotient. You have to remember the quotient rule first of all, but then also the top of this quotient is itself a product. And so you have to do a product rule and the quotient rule kind of simultaneously. It's a product rule inside of a quotient rule, which is kind of a mess. Instead, you can do what we call the logarithmic differentiation technique, and that is do the natural log on both sides. It now says ln y on the left and on the right, ln of this big fraction. X squared times 7 plus x to the 10 divided by that business, like so, right? Do the natural log on both sides, and now I am going to simplify on the right as much as we can. And here is the step in which you can see kind of the product and the quotient just sort of go away. All right, we're going to simplify on the right using our rules for the natural log. First of all, the big quotient I can change into subtraction. That is the rule about natural log. So here I'm using the rule, ln a over b equals ln a minus ln b, right? That's what I just did there. I had a fraction, but I turn it into this. That's the step where the quotient rule is kind of done away with. And then we can further simplify. Actually, the second one here, this cannot be simplified anymore. Log of a bunch of stuff added together doesn't simplify. But the first one can, because this is a product on the inside. X squared times that other thing, I can do the log rule about products. This will say log of x squared plus log of 7 plus x to the 10, like so, minus this thing you can't improve at all. And then one more step, I can bring the exponents inside the logs down to the front. That was our last property of the natural log function. So this becomes 2 ln x, right? Each of those exponents on the inside can come down into the front as a coefficient. 10 ln 7 plus x, and then this last one has to stay as is. And I'll just copy the left-hand side. Remember, all of these things equal ln y, all right? This is the logarithmic differentiation trick. It's because it changes some kind of complicated quotient and product into just a bunch of things added together. And now we can do the derivative on both sides. So now, take the derivative on both sides. And for this, you do need to use the chain rule, but they're like very easy chain rules. Use the chain rule. So on the left side, ln y becomes 1 over y times y prime. That's the chain rule. It's 1 over y because the natural log of y, you know, the derivative of ln something is always 1 over whatever. And then the chain rule, I have to multiply times the derivative of the inside. So 1 over y times y prime. If you like, this is called the implicit derivative you may have heard of. We're not going to do a lot with the implicit derivative in this class, but that's that. Anyway, on the right-hand side, what is it? 2 ln x, the derivative is 1 over x plus 10 ln 7 plus x is 1 over 7 plus x. We have to do the chain rule on this one, but the derivative of the inside there is just 1, right? The inside was 7 plus x. The derivative of that is 1. And then finally, minus ln of that business becomes 1 over that stuff. 1 over 5x squared minus 7x plus 4. And then the chain rule times the derivative of the inside would be 10x minus 7. That's the derivative of this stuff. It's 10x minus 7. All right. And we're almost done here. Of course, what I'm looking for is y prime. That's the goal of this whole thing, would be to take the derivative of the original thing. So I'm going to multiply the y onto the other side. So it says y prime equals y times, and then all of that stuff. Maybe I'll just sort of clean it up a little bit as I go. 2 times 1 over x, I'll write that way. And then 10 over 7 plus x, and then 10x minus 7 over 5x squared minus 7x plus 4. All right, and finally, last step. This is pretty much the answer, but I don't want a y to appear in the answer, so I can plug in, though, where we started, all the way at the top there, you can see y equals this stuff in terms of x. So to write my final answer all in terms of x, I'm just going to replace y with that. So it will say, this is my final answer. Y is all that stuff that we began with at the very beginning. X squared 7 plus x to the 10 over 5x squared minus 7x plus 4. And then times this stuff. 2 over x, 10 over 7 plus x, 10x minus 7 over... Like that. All right. This is my final answer. It's a bit of a journey, and I don't know, like I said, this is a cute technique to avoid doing product rules and quotient rules. Now, I will sort of leave it up to your own judgment. This was like a lot of steps that I had to write down. Maybe you're feeling like would have been easier to just do the product rule and the quotient rule to begin with. In my opinion, actually, this is easier. It looks like a lot of work, but if you think about if you know what's going on, you can skip many of these steps. For instance, I can look right here. What I see is this times this divided by that. I can immediately jump to this step and say it's the first thing times the second thing, and then, it'll be the log of the first thing plus the log of the second thing minus the log of the third thing. That's this. And in fact, I can also jump straight to this step, really. So if you know what you're doing, you can basically go from here all the way to here in your head. And then from there, you take those derivatives. All these logs just turn into 1/overs. This is also something that's very easy to do in your head if you know what you're doing. So it looks like a lot of work that I did here, But practically speaking, this actually is a very useful technique, especially if you have even more complicated things like this. You can handle very easily using this trick. All right, so I have one that I would like for you to try, and I think that will do it for us today. So try this one here. Two x minus 1 times 3x squared minus 7x. See what you think. Do the same kind of a trick to find the derivative of that. that's only from this part. There should be stuff from the others too.
Still good here? It's not wrong. I would have instead just done straight.
Yeah. All right, let's chat about this one. So, this being a big quotient, when I make the logs, I'm going to do logs on both sides, right? Here, I'm gonna try and dazzle you with my. Like I said before, if you know what you're doing, you can kind of do a lot of these steps in your head. When I'm going to take the log, I see a quotient here. That means it's going to be the top minus the bottom. But the bottom is a product, so the bottom I can also write as two things added together. Or equivalently, it can be the top minus this and also minus this. So it's going to turn into log of x to the 4 minus log of 2x minus 1 minus log of 3x squared minus 7x. This is how I would start off. Then I could bring the 4 down in that first one there. Log of x to the 4 is the same as 4 ln x. Actually, you can probably even do that in your head just from the very beginning. These other ones you cannot simplify, right? Don't try to like pull this 2 out, or even this squared here cannot come out. It would have to pull out a squared, it would have to be the entire thing squared, but it's not. It's only the first part of it, so you can't do any of that business. All right, anyway, now I'm going to do the derivative on both sides. I get 1 over y times y prime on the left, and here my derivatives look like 4 over x, 2 over 2x minus 1. That's the chain rule, right? 2x minus 1 goes into the denominator, and then I have to multiply times the derivative of the inside, which is 2. That's why I put a 2 there. And then the last one is going to be 6x over, sorry, I forgot this x here. There should be an x there. That was a typo. 6x minus 7 over 3x squared minus 7x. All right, that's the derivative of that last one. And then you multiply the y to the other side, and then plug back in the original formula for y. Would you mind if I do that all at once? It will say, here's y. X to the 4, 2x minus 1, 3x squared minus 7x, and then times that other stuff. 4 over x minus 2 over 2x minus 1 minus this guy. That's it, all right? You could, of course, check your answer by doing the product rule and the quotient rule, although it would look totally different from this. If you actually do the product and quotient rule on that, you will get this, although it will be written in a very different form, and it'll be more trouble than it's worth to verify that they're equal, but they are. All right, I think that's enough for today, if you don't mind finishing it.